Okay, so today we are learning about the combined gas law. And so before we can talk about the combined gas law, we are going to talk about the three laws that we learned about. So yesterday you should have watched 3 demonstrations that we did in the lab. One covered Boyle's law, one covered Charles' law, and one covered Gay-Lussac's law. And then in class, we went over the definitions of each of these laws. And on those slides, they had some mathematical equations. And we didn't do the equations for each of these. However, you do not need to write these ones down. Okay, so this is the equation for Boyle's law, Charles' law, and Gay-Lussac's. Okay, so instead of having to memorize 3 different laws, we actually can put these all together into what we call the combined gas law. And that is what we'll be using today. Okay, so you do need to write this formula down. Okay, and it's called the combined gas law because it combines each of these into one formula. Okay, so looking at this formula, we have 3 different variables that we're using. Our capital P is our pressure, our V is volume, and our T is temperature. Okay, and anytime we use temperature in chemistry, we always want it to be measured in Kelvin. Okay, so even if it's in Celsius, we always want to convert it into Kelvin right away. Okay, another thing you might notice about these formulas, or this formula here, is that it has subscripts. Okay, those little numbers at the bottom. These subscripts represent kind of like a before and after. Okay, so the subscript of 1 is the measurements of your gas before a change occurs, or you might also see it as like the initial measurements. And the subscript of 2 is the measurements after a change occurs, or your final measurements. Okay, so think about your left side of your equation as like your before, and this is your after. Okay, another important thing to know before we get started are some important conversion factors. So right now, I'm writing the conversions for our different units of pressure. And this is something that was already in your notes from Monday. But it's always good to have it handy when you're doing any type of like gas law calculations. Another important one is how to convert Celsius into Kelvin. Okay, so these are our conversion factors. Okay, so what I would recommend whenever you are doing any type of gas law calculations is to always have your formula and your conversion factors written at the top of your paper so you can always have them available to you. Okay, so let's go ahead and get started on our first practice problem. So our first practice problem says a gas has a volume of 0.8 liters at 250 Kelvin and 300 torr. What would the volume of the gas be at 500 Kelvin and 1 atmosphere? Okay, so what I want you to do first is identify all the information that you know about your gas initially. So we know that our gas has a volume of 0.8 liters. It is currently at 250 Kelvin, and it has a pressure of 300 torr. Okay. It is asking what the volume would be at 500 Kelvin and 1.2 atmospheres. Okay, so what we did to the gas is we increased its temperature from 250 to 500, and we increased its pressure from 300 torr to 1.2 atmospheres. Okay, so after we increase the temperature and the pressure, what we want to figure out is how that will affect the volume. Okay, so the volume is what we are looking for. Okay, now I'm going to copy this information into a T-chart that I'm going to label before and after. Okay, so my information that I know before is my volume. I know my temperature. And I know my pressure. Okay, and then my after, I know my temperature. And I know my pressure. Okay, I have a blank right here because I do not know my final volume. Okay, that is what I am looking for. And so a couple things that you want to make sure about your information before we get started is, number one, that your temperature is in Kelvin, which it is, so we're good there. And you want to make sure that all of your units match. Okay, so we want Kelvin and Kelvin, which we have. However, our pressure, we have two different units here. Okay, so we need to either change them to torr and torr, or atmospheres and atmospheres. Okay, so I'm just going to choose to convert this atmospheres into torr. And to do that, I'm going to use the conversions that I wrote on my first page. Okay, so it says that 1 atmosphere is equal to 760 torr. Okay, so to convert this into torr, I'm going to start with what I have, what I'm given, which is 1.2 atmospheres. And then I'm going to draw my chart. Remember, I leave this bottom part blank. And then whatever unit I have up top, I'm going to put in the bottom of the next section. Okay, so I'm going to write atmospheres down here. Okay, and then I'm going to convert my atmospheres into torr. So that's what I want to put on top. Okay. To fill in these numbers, I'm going to use my conversion. Okay, and I see that 1 atmosphere is equal to 760 torr. Okay, these units cancel, and I have found the unit that I'm looking for. So I'm going to go ahead and solve. And to solve these types of problems, you multiply everything that's on top of your chart and divide by everything that's on the bottom. Okay, what's on the bottom of my chart is a 1, so I'm actually just going to ignore that, because if you divide by 1, you get the same answer. So I just need to do 1.2 times 760. I do not have a calculator. And when I multiply those, I get 812 torr as my answer. Okay, so now I have converted these atmospheres into 812 torr. Okay, now that all my units match and I have my temperature in Kelvin, I am ready to write down my formula, plug in my answers, and solve. Okay, so my formula is, so everything that is in the left side of my before and after chart will go in the left side of my equation. Everything on the right side will go on the right side of my equation. Okay, is equal to my pressure of 812. I don't know my volume, so I'm just going to leave it as V2 and divide by 500. Okay, so the rest of this is just algebra. Okay, it's just solving an equation with one variable. Okay, However, to do that, I need to isolate this variable, okay? So let's actually go ahead and simplify this side first, just so we have less numbers to work with. So okay, so when I multiply 300 times 0.8 and then divide by 250, I get 0.96 equals 812 V2 over 500. Now to isolate the V2, first I have to get rid of this 500, okay? Now, 500 times 0.96 gives me, and I'm still left with 812 times V2. And so to get rid of this 812, since it's currently being multiplied, I need to divide it. .59, and my unit is liters. And I know my unit is liters because that is the unit of volume that I started with. Okay, remember your units always have to match. Okay, so that answer is 0.59 liters. Okay, so my second practice problem says 600 milliliters of a gas is at a pressure of 8 atmospheres. What is the volume of the gas at 2 atmospheres? Okay, so my gas starts out with 600 milliliters at 8 atmospheres. And then I change the pressure to 2 atmospheres. Okay, and as a result, the volume is going to change, but I don't know what it is, so that is what I'm looking for. Okay, now I'm going to draw my before and after chart. Okay, so I know my volume and I know my pressure. On my right side, I don't know my volume, but I do know my pressure. And what I'm looking for is my V2. Now I need to make sure that my units match, which they do. So now I'm ready to plug in and solve. So I'm going to write out my equation. And what you might notice is that my problem didn't give me any information about the temperature. Okay, and if that ever happens, you just assume that that temperature stays constant, and so we can actually ignore it. Okay, so now I'm just left with P1 times V1 equals P2 times V2. Now I can plug in and solve. Times my P2, which is 2, times my V2, which I don't know, so I'm just gonna leave as a variable. Okay, to solve this, I just need to get rid of the 2, which is currently being multiplied. So I will do the opposite and divide. Then I have V2 is equal to 8 times 600 divided by 2. You always want to make sure that you include your units. And so what I started in was milliliters, so that is the unit that I found. Okay, so my final answer is 2,400 milliliters. Our third practice problem says at 27 degrees Celsius, a gas has a volume of 6 liters. What will the volume of the gas be at 150 degrees Celsius? So just like the other problems, I'll identify what I know about my gas initially. And I'll also identify what I know about my gas after the change. So I know that I increased my temperature from the before. And so I'm going to be looking for the volume. Okay, so now I'm going to write these into my before and after chart. I know my temperature and my volume after my temperature, and my volume is still unknown. So that's what I'm looking for. So all of my units match. So it looks like I'm ready to get started with my equation. However, if you remember, temperature always has to be in Kelvin. Okay, so I am going to immediately convert these Celsius temperatures into Kelvin. So 27 plus 273 gives us 300 Kelvin, 423 Kelvin. Okay, and now I'm ready to plug that into my equation. Do I know anything about my pressure? No, so I'm going to cross those out, and that leaves me with V1 over T1 equals V2 over T2. Okay, I'm gonna plug that in. Okay, so this setup may look familiar to you because this technically is a proportion, okay? So you can either solve this by multiplying both sides by 423 to isolate this variable and then simplify, or you can cross multiply and divide, okay? Both will get you the exact same answer. So I'll show you how to cross multiply and divide it because that seems what most people are more comfortable with. So I'm gonna cross multiply by my 423 times 6, which is equal to 300 times V2. And then I'm going to divide both sides by that 300. So I'm going to plug into my calculator. 423, I know y'all can't see that because of the glare. Divide by 300. And so I get my answer as 8.46. And I'm going to double check that unit, and it's liters. And that is my final answer for that problem.